right. Of course, not working. So 5, 3. Well, it's two more. It's two final distributions. Well, I shouldn't say that. Two distributions that just gives us probabilities and not inferring, not doing constant intervals and stuff will be coming up to. But two further distributions we're recovering is the binomial distribution. And shorthand notation for that is going to be, B for binomial, X, P. Well, P is the probability of, well, look for success or failure. Probability of success or failure, depends what you're looking for. And X is basically number of events, number of events, or value being looked for. And of course, this stands for binomial. All right. Now, what's meant by binomial? Well, to say maybe the right probability, there's two B's of probability. To say me all the writing, I'm going to pull up and I will make this available to you on Blackboard. So to even consider using a binomial distribution, bi means two, we have to meet a couple wickets. Couple gates have to be crossed. Gate 1, data has to be discrete versus continuous. So we're talking about counts. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, ad infinitum. Okay. So the data has to be discrete for starters. Okay. Being binomial, we have to have only two possibilities. And I threw up some examples. Something it's either good or it's bad. You accept, you reject it. You survive, you die. Correct, wrong. Okay. So there has to be a definite this or that happening, be looked at. A lot of times, like rolling a die, you roll with a 5 or not 5. That's a binomial. I'm rolling a dice. I either roll a 5 or I don't roll a 5. And of course, the not 5 includes the 1, 2, voting a 1, 2, 3, 4, or 6. Must have a fixed number of trials. You just can't keep doing it forever. Yeah. And you can also figure a fixed number of trials being the sample size. In this population, I have a probability of rolling a 5, 1 out of 6. rolling a 5 on a third die 1 out of 6 times. What's probably rolling a 5 3 times out of 8 rolls? Sample size 8. All right. Trials. So we have to have fixed number. Trials have to be independent. So the event, the second event, isn't influenced by the first event. This kind of goes back to part 2. Each trial falls in 2 categories, either success or failure. Basically, P and Q. And of course, the probability of P success plus the probability of Q failure, of course, has to add up to 1. Okay. And probability of success remains the same in all trials. So as this kind of relates back to 4. If the trials are independent, then 6 should be true. Probability of success remains the same in all trials. The probability doesn't change over time. Like so, I'll have this. I'll have this. I'll put this up in Blackboard. Yeah, I'll do that right now. Each one, pull it up. Should have done this already. Do it now, so later. That should be it. Yep. Okay. That's good. So you want to go and open up? Be my guess. And you go along with it. All right. All right. So those are the wickets that need to be met. Okay. Kind of a summary. Fixed number of trials, and trials are independent of each other. That kind of goes back with item 3 and 4. This is basically number 3 and number 4 re-emphasized. All right, now here's another thing you need to ensure when you're doing the binomial. If you meet all those requirements, if the data is discrete, if there's only 2 outcomes, if the number of trials are fixed, if they're independent, and everything falls into 2 categories: success or failure, and success in the trial, probably success remains constant on a trial. You also have a quantity, a sample size number. Okay, population size. First of all, you need a population. Okay, large enough. Okay, and because with that population you're going to draw your samples from, you want n to be no greater than 5%, or think of it as 1/20th. So you don't want your sample size for binomial distribution to be too big. For binomial distribution, you want your sample size to be no more than 20%. I'm sorry, 1/20th or 5% of the population. So you're drawing from a sample size of 100. You want your n to be no bigger than 20. If it's bigger than 20, you got to go to more to an you got to do more of a normal approximation then. All right. So you also got to then check that. Hey, I'm drawing a sample. I'm looking at 30,000 people. I want to do a sample of 500. Well, it's 300 divided by 500. More than 20. Or 30,000 by 5 more than 20. Then you can't use binomial. Let's see. Some notation for binomial distribution. Basically, we can use S and F for success and failure. So probability of S, we'll call little p. Probability of success. Probability of F failure, we'll call Q. And of course, probability, if probability of success is P, probability of failure has to be 1 minus P, which we call Q. So if we have N as a fixed number of trials, X represents the number of successes in N trials. Like I said, I'm rolling a die 8 times. What's probably of having 3 of them come up 5s? Okay, P and Q is the probabilities of 1 trial. And the probability of X is probably getting exactly X successes among the N trials. All right. And of course, these numbers have to remain constant between trials. Okay. So every time you do a roll of the dice or whatever, it should have the same distribution, the same probability. And of course, the formula for it, formula for the probability of X is n factorial over the quantity n minus x factorial divided by x factorial times probability of success of 1 success to the x times the probability of 1 failure to the n minus x. Right. If you're going to do this by hand, that's basically is the same equation for doing a finding a number of combinations of a value. Okay. And more of the details. All right. By hand, this could get quite awkward by hand. So in solving these, we have 3 methods. Tables to a degree, by hand, means this way, or technology. Technology. And I'm going to do an example in class where I'm going to use all 3. Tables and hands aren't bad, are reasonable if A, the number you got to compute isn't that large, and B, if there's a table that covers it. Tables is always the issue. I mean, it's very specific on what P and Q can be, and it's also very specific on how many trials, what N is, number of trials. I also have this post. It's just a quick Excel sheet that has basically the equations all a little more compactly written up. All right. So binomial distributions, pretty reasonable. Not that over the top. Do. I spoke of tables. This is a typical table. And here we have number of trials. For success, 1, n equals 1, n equals 2, n equals 3, n equals 4, and so forth. This is going to work. No, it doesn't. Oh, darn it. So let's see, you go from specifically your probability of success of 0.010. So if you happen to have a problem that has one of these values for success, or failure for that matter, okay, tables are an option. And of course, how many trials you doing? As long as you don't go over, you should know this one, over 20, as long as you don't go over 20, and your probability of success or failure is one of these guys, yeah, you're good to go. If not, you either got a hand calculator or use technology. Let's look at these guys. So what is the table telling me? So if I do a single roll of the dice, that's not a good one. Let's say I'm picking I'm picking a random number between 0 and 9. 0 less than equal to x less than equal to 9. Okay. Which means my sample size is 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 as terms of digits, in terms of unique values, is 10 of them. And if it's each value 0 to 9 has an equal probability of being picked, that means the probability of a specific value of x is going to be 1 over 10, or 0.1. Which means P is 0.1. So I do one roll, okay, and I want to, or one cycle of doing my random generator of 0 through 9. The probability of 1 should be, okay, is probably 1. Q is 0.1. Or I'm sorry, P is 0.1. So probably rolling a 1 would be probably success. 0.1. Probability of failure. Probability of failure of not rolling a wanted number, 0.9. If for some reason, that'll work. For some reason you have a bias put into the value, such that the probability of having x equal to 3 is 0.35. Well, there you go. Probably rolling that specific number of 3 is 0.35, and of course 0.65 for anything but the 3. If you look at any of these columns, pick a column, any column, they should all add up to 1. They should all add up to 1. So we're going to do an example. I'll do an example that will use the tables here. These guys, if you want just for fun, look back at the book at the probability binomial distribution table in the textbook, and just pick an arbitrary column and add them up, see what you get. Do an easy one here. 0, 0, 4 plus 2 is 6, 6 plus 4 is 10. 6 plus 1 is 7, plus 3 is 10. Adds up to 1. That's got to happen. Because basically, this is your sample space here. Sample space is rolling, is getting 0 of them, 1 of them, 2 of them, or 3 of them. Let's go back to the original 0.1. This is so weird. I want to roll. I'm going to run the random number generator 3 times. Okay. So what I can use this for is, okay, what's the probability of rolling, of having x equals 2, okay, x equals 2, what's probability of having all 3 of them come up as 3? So I have 3 numbers. What's probability of having 3 come, a 3 come, and a 3 come? 2. I'm looking for 2s. What's probability of the random generator giving me 3 2s? Well, here's my P. Probability is 0.1. They have it happen 3 times. It's 0.010. What if I want the probability of having exactly 2 of them come up as 2s and something other than 2? Well, what's the probability of having it happen twice? Well, that's 0.0270 times of it occurring 2 times. All right. So that's kind of like how I use the tables. So let's do some problems. And what I would like to look at the textbook in problem 5.61. 5.61. So let's pull that up real quick. I'll look real quick here. 61, here we go. Hopefully I can run this thing. Oh, good, it does. Excellent. All right, so I'm gonna let you take a minute to read it. You take a minute to read the problem. How am I going to do this? Okay. So let's see. A survey more than 20,000 U.S. high school student survey revealed that 20% of the students say that they stole something from a store in the past year. All right. This is down some percent from last survey, which was from 2 years earlier. You decided to take a random sample of 10 high school students from your city and ask them this question. All right. So population. Okay. Looking at 20,000 high school students. Sample size. We'll look at 10 of them. Okay, now, first check number one. Check number one. Is 10 less than or equal to 5% of n? Or is 10 less than or equal to 20,000 over 20, which is 1,000? Yes. All right. So you can consider a binomial. Okay. 20% of the students says they stole something from a store in the past year. What's the two situations I've got? Basically, you stole or you didn't steal. So it is binomial because I'm looking at students and there's two things. Either they stole or they didn't steal. With probability of success would be 0.20. Probability of failure 0.80. And it's 1 minus 0.2 because you got to add to 1. Like I said, your success may not always be a good thing. So we have n equals 10. We have two distinct things we're looking at: success or failure. Success being they stole, failure being they did not steal. We do have discrete numbers. No students, 1 student, 2 students, 3 students, 4 students. You can't have 1.1 students. It's down some from last year, but okay, that's extra stuff. So part A is pretty easy. It says if the high school students in your city match this 20% rate, what is the distribution of the number of students? Okay, what they're looking for in this case is binomial distribution. The binomial distribution of 10 students at a success rate of at a probability of occurrence of 0.20. That's all they're asking for that guy. And they say, what's the distribution of the number of students who do not say that they stole something? Okay, well, still out of those 10 students, it'd be the complement. Remember, the binomial is going to be the sample size and then probability. Remember, distribution or Q if you look for the other guy. All right. That's A. So far, pretty tame. B, what's probably that 4 or more of the students in your sample say that they stole something from a store in the past year? Ooh, that's a little more involved. So probably that 4 or more students in your sample said they stole something from a store in the past year. I'm looking for the probability of X greater than or equal to 4. Means the probability of X equals 4 plus the probability of X equals 5 plus probability of X equals 10. So that's 4, 5, 6, 7, 8, 9, 10. That's that's up to 7 calculations. But we know what we learned something earlier is we can use the complement rule. Because this will also be equal to 1 minus the probability of X less than 4. Well, 1 minus the probability of 0, minus probability of 1, minus probability of 2, minus probability of 3. That one doesn't look very good. Okay, how do you erase from this guy? It works. No, I just overwrite with black. That's only 4 calculations. And 0 is always an easy one to do. Okay, so we only have to do 4 calculations. Probably 0, probably 1, probably 2, probability 3. All right. And unfortunately, I can't do an extra page here, so what we're going to do is, that's not what I wanted. All right. This I can add to. All right, that's not bad. Actually, was pretty good. All right. All right, remember, again, let's go back to the binomial theorem. By hand, probability of X is not that one. Is n factorial over n minus x factorial, all that stuff. All right. Come on. Oh, backwards. And then PDX, Q the n minus x. All right. Alex, this is NC as written. What a value for n, what a value for x. You use a combination tool. All right. So what's probably 0? Probably having 0 kids saying they've stolen out of a sample size of 10. Sample size of 10. The probability of them having say they stolen is 0.20, and none of them stole. What's the probability of that happening? Well, plug the numbers. I'll have 10 factorial over 10 minus 0 factorial, 0 factorial, times 0.20 to the 0, 0.80, 1 minus p, to the 10. And in case you're wondering where to find that NCR tool on calculator, it'd be under, I believe it's under the math. So it'd be under the math key, roll it over to probability, and there it is. There. Depending on your calculator, you may have to enter. Sometimes you have to put in that value, then pull that guy in and enter x 0. This one isn't for you. And I know the answer. The answer is going to be 1. The answer is 1. So let's see. We have basically it's 10 factorial over 10 factorial. 1 times anything raised to 0 power is 1 times 0.80 to the 10th, which comes out to, what's my numbers at? 0.1074. So do sample size, out of 20,000 students, you do sample size of 10 from your school. You expect out of 10, no, 10%, roughly 1 of them to say, no, I didn't steal. Now hold that number. Hold that number. Actually, yeah, that's right. Let's go to binomial table. Probably 0.2. N equals 10. 0.2. And look what we got. 0.1074. Same number. 0.1074. It works. Probability of 1. Well, that would be 10 factorial. Again, 10 minus 1 is 9 factorial over 1 factorial. Times that 0.20 to the 1, because x is 1. And what the equation is, I'm looking for x equal 1 times 0.80 to the 9th. 9 plus 1 is 10. This will give you a 10 times 0.20 times 0.80 to the 9th. And that comes out to, I'm going to do it again, 0.2684, I believe. Again, you look at the table, again for 0.20 and 10, 0.2684. So if you have the table, if you have tables available, again, they're limited. You got very specific values for P and very specific numbers of N. You can avoid doing all the hand calculations. And if you go on by hand, you'd find that P probably of having two of them would get you 0. Maybe 10 factorial over 9 minus 2, 2 squared 8th. Again, just plugging in the values for P, Q, and the X's. And that's 0.3020. Lastly, probably of having three of them. 10 minus 3 is 7. 3. Probably the success is 0.20. 3 of them. Probably of failure, 7 of them. And that gets you 0.2013. Here are those numbers. And again, 3020, 2013. So you have to say, so the numbers are in the tables, the exact same numbers I generated using the formula for it. And so real quickly, that'll equal, let's see, 8, 5, 3, 2. That should be 30. This should come out to 30, all right? And what factorials are is basically saying I want to multiply together all those numbers. That's 10 factorial. 7 factorial, we're going to reverse a little bit here, just for convenience. 7 factorial is that. Of course, all of these numbers will cancel out all of those numbers, multiplication here. And 3 factorial. Oh, I goofed. It's not 30. I made a slight boo-boo there. Maybe I'll have to take a look. Oops. That 3 will cancel out that. That cancels out that. Oh, 120. I think I did 5 times 3 times 2 or something like that. I forget what. Mentally. All right. So that's what's happening. Is factorials have a lot of cancellations, so they're not hard to do by hand. Knowing that, I mean, you can almost avoid the right-hand stuff, because knowing that, I know what 10 factorial is. I know that 7 is going to take out everything from 7 below, which means I could restart knowing that 10 factorial, 7 factorial gives me that. Then 3 times 2 times 1, and then do quick cancellations. Always got a lot of cancellations for 120, all right? Getting back to this problem though. Or just use the calculator. Use the calculator. Where's it at? Would help to have the right one. Ten, 3, 120. You can always use that too. And I would not blame me if you do, to be totally honest. All right, so let's finish the problem off. So what's the probability of, remember the original question was, probability of having 4 or more students say they stole. Okay. This was the problem, wasn't it? That 4 or more of the 10 students stole. So now we got to basically add all these guys up. The 0.1074 or 2684 or 3020 and 2013, add them all up. And that adds up to 0.8791. So final answer, probability of X being greater than or equal to 4, 1 minus probability of X less than 4, or 1 minus 0.8791, or 0.1209. Right? So 8791 is the probability of having either 0 students, 1 student, 2 students, or 3 students say that they've stolen. Okay. So that's a mixture. Okay. This is out of 10. How many probably of having exactly 3 students say they stole? 0.2013. 20% chance of having exactly 3 students say they stolen. Probably of having exactly 2 students. Okay. The probability of having either 0, so the probability of having either 0, 1, 2, 3 students is just under 88%, 0.88, which means just over 12% would have been either 4, 5, 6, 7, 8, 9, or 10 students would have said it's stolen. If you look at the probability distribution, in a given population of 10 students, really probably of having out of 10, like 5, 6, or 7, or 8 students is pretty small, which is, I guess, good to know. But then only 20% said they stolen. Maybe not exactly. This other guy. Right? Okay. So I want to do more on this problem and do some Poissons, but they're going an hour, so I would like to take a short break. Basically, I take a short break, about 10 minutes. Hi. Seeing from the store continued. Refer to exercise 5.61. I need this guy here. All right. And I'll have this posted also. Oh, binomial NP. All right. So this is basically the PDF file that I have on file for you all. Okay. But with a binomial distribution, Okay. Basically, knowing N and P, remember what N is. N is sample size, and P is a probability of that sample of success within that sample. So the mean is something very simple. It's just a sample size times the probability of what you call success. The variance is the sample size times probability of success times probability of failure. And of course, standard deviation is the square root of NPQ, square root of variance. So, hey, it's pretty easy math. Hey, I know I have a sample size. I have a probability of something occurring within that sample size. So my mean or expected value, call it mean, and I'll say expected value. In this case, would just be NP. So, shoot. Let's grab a quick picture of that one. Oh my. All right. That's what we're going to need for solving this problem. So, what is the expected number of students in your sample? You call the sample, N was 10, P was 0.20, and Q was 0.80. Okay. What is the expected number of students in your sample who say that they stole something from a store in the past year? So for this A, I'm looking for mu NP, and of course N is 10, P is 0.20, so I would expect that in a sample size of 10, there will be two students who will say, yeah, I stole something in the last year. Let's see how that compares to the probabilities. And just by happenstance, it looks like 2 is the highest probability. So a general observation should be about where the mean is should also be the highest, within the region of the highest probability. So let's look at one more over. Let's just check, do a check here. Let's look at 0.4. Well, 10 times 0.4 is 4, so x equals 4. And that's the highest, highest probability. 0.5, give it x equals 5, that's the highest probability. So yeah, generally speaking, where you come for the mean, the expected number, generally also occurs on probability distribution, the highest probable value of occurrence. Okay. That's just an observation I've made over the semesters. Okay, that was A. B, what is the standard deviation of the number, sigma, of the number of students in your sample who say that they stole something? Well, sigma of the sample, of the population, NPQ, or 10 times 0.2 times 0.8, I think is 1.6. And its square root of 1.6 is 1.265. So roughly round 2, I have standard deviation of about 1.265 students to do a normal distribution analysis, approximately normal. Suppose you live in a city where only 10% of the high school students say that they stole something from a store in the past year. All right, so now for C. Now C is 10, N is 10. Now P is 0.1, which makes Q 0.9. What's sigma going to be? Well, so NPQ, so 10 times 0.10 times 0.90, which I think is 0.9. And its square root, take its square root, you get 0.949. What would sigma be if P is 0.01? Okay. So still N is 10. 0.01. So Q would be 0.99. N times P times Q. That gets us to 0.099 or 315. So generally speaking, as P gets smaller, looks like, oops, sigma gets smaller. Interesting observation. And I forgot to show. So that's basically using all the equations for a binomial distribution. I forgot to show one thing though. How to do this on a calculator. Oh, okay, that's fine. On a calculator, I mean, we have under distribution, so it blue is distribution, so second bars, and if you go down, you're going to see a couple. I have binomial, and we'll also go and Poisson. Both cases, Poisson or binomial, PDF means a single point distribution, while CDF is going to be a cumulative from left to right, from basically zero to where you want to go to. So let's do the binomial for a little bit for change. And that's there we go. So let's do a single binomial distribution. And get rid of these. So let's see. We have trial 10. We have 10 trials. Okay. Probability of success, 0.2. Look for x equals, let's go with 1. Okay. And what do we get? 0.2684. Here's a probability of 1 occurring, 0.2684, 0.2684. So calculator works. To get a, want to get a range of them, we want to use the cumulative. We want to do more than one, do cumulative. Okay. And it's going to go from, always go from 0, cumulative ones from 0. So again, trials. 2, 0. I want to go up to 3. So I want 0, probability of 0, probability of 1, probability of 2, probability of 3. $27.91. And of course, 1 minus that will give us probability of 4 and greater. 1208, 1209. So again, on the distribution, second distribution, we can do a single specific probability of occurrence, a value for x, 0, 1, 2, 3, up to n. We can do a cumulative one that includes 0, 1, 2, 3 to x. Now, unlike the normal distribution where we can go between a low and high, the binomial and Poisson always starts from 0. So if you ever want to find the value between x equals 3 and x equals 10, you're going to do cumulative 10 minus cumulative 2, I guess, to find 3 to 10, or something like that. Okay? So again, you can also do it in the calculator via second distribution and scroll down to find your, binomials. A single value or cumulative 0 to a value. That was it? Looks missing. Oh, yeah. There you go. And let's see, how do we do? How do we do? 61. Oops. Here's what I want. There you go. Here's 2. 8 was here, not stolen. Okay. 1265, 0.949, 0.215. Is that what we got? 2, 0.315. So we got those numbers successfully. And as p gets smaller, standard deviation becomes smaller. Gotcha. All right. Okay, let's look at Poisson. The Poisson distribution. And this is also in Blackboard now. A Poisson distribution is unusual. Okay. And a Poisson distribution works over what we call an event over some interval. And the intervals are unique. I have some examples here. A time, area, volume, distance, or some other type of unit. Okay. It's not so much a mass, pounds. It's not like pounds or inches or feet. Okay. I don't know how else to describe it. but usually we're talking about like something within a time, area, volume, and distance. We can possibly do a Poisson interval. All right. Must be random, as before. They must be independent of each other, and the occurrence must be uniformly distributed over the interval being used. Essentially, this means that a mean exists for the distribution. And it's best to show that with an example. Another interesting thing, and I'll do that on the next one. Okay. Now, to do a Poisson, if the occurrence is over an interval, all right. Example: in the hurricanes over per month, or a number of colonies of bacteria in a certain area per unit area. The distribution of, where this was on World War II, distribution of bomb hits over a given area of London. Break London up into areas, you get a distribution. Okay. Formula for it is pretty easy. If you look at it, the only thing we need for a Poisson distribution calculation is the mean, number of occurrences, number of occurrences. That's it. If I know what I'm looking for within the interval, how many times five of these will happen, or 8 of these will happen, and it has an average rate of mu. That's all you need for Poisson. You don't need standard deviation, because standard deviation for Poisson is just the square root of the mean. All you need is the mean. That's it. So let's keep that in mind. I do want to copy this guy down for. I'll call it posterity. Okay. Oh yeah. Another thing about Poisson intervals is the means are additive and scalable. What do I mean by that? Say we had I don't want red. Say we had a petri dish of 8 square centimeters, and there was a mean colony distribution of a mean. So in this 8 centimeter square, there was a mean of 20 colonies. Right. If I was to scale this up to a 32 centimeter square petri dish, and everything else being the same, this one should have a mean of, 4 times as much. If I was to take this 80 and I would add it, say this mu was 15. And let's combine the two. I should be able to claim this as being a 78 centimeters squared with a mu 35. It's weird. I don't know why it works the way, but it does. What that problem? Did I post a problem? I did not. So what I like to do is look at a problem. If I can find it now. Let's close that page out. Problem 81. All right, there we go. Problem 81. Yeah, let's read it. English Premier League goals, the total number of goals scored per soccer match in the English Premier League often follows the Poisson distribution. So in one recent season, the average number of goals per match, okay, so here's the average, here's the interval, mu is per match or per game. So over the interval of a game, the average number of goals scored was 2.768. Okay, so my interval is per game with a mu of 2.768. That's it. Now the question is, what's probability that 3 or more goals are scored in a game? Wow. So here's this between binomial and Poisson. A binomial, we got to have a fixed number of trials. Can't go on forever. With Poisson, there is no upper limit. Technically speaking, is there a limit to how many goals can be scored in a game? By both sides combined. This is a combined score, by the way. Both sides. And theoretically, no. Other than there is a limit of how much time you can play it in to do a game. But really, there's no upper limit. So Poisson's goes from 0 occurrences up to infinite. So see, A is what's probability. So P of X, with this Poisson, it's going to be 2.768 to the X e to the minus 2.768 over X factorial. And just in case you don't know that, oops, 0 factorial is 1. I thought I mentioned that the other day, but I'm not positive. So there's my Poisson distribution. So give me the X's and I can give you tell me how many goals you want. 0 goals, 1 goes, 2 goals, 3 goals. I can tell you what the probability of it happening is. Let's look at A. Probability that 3 or more goals are scored. which means 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 100, 200, 300, 400, 500 goals. Now, eventually this guy goes to 0 when it gets big enough, but it depends what mu is. So that's going to be hard to do. So it's better to do 1 minus probability of x less than 3. So it's probably having 0 goals, 1 goal, 2 goals, and subtracting that from 1. Much, much, much easier calculation. And really, these aren't that hard calculations to do. Because one set, this guy's a constant. So let's figure probability 0. You know, it's 2.768 to the 0 power, which is 1, times e to the minus 2.768, which is a number, over 0 factorial, which is 1. And if you crank the numbers in the calculator, get 0.6, 0.0. 0.06279. Do for 1. Over 1 factorial, which is 1. So really, this will just be, take this number and multiply by 2.768. Because P of 0 is essentially that number. And all I'm doing is probably 1 is multiplying by one of these guys. So that's basically what you get. So this is 0.1738. And probably have 2 goals being done. Again, you put those numbers in, turn the crank, and you get 0.2405. Add them all up. This guy, this guy, and this guy. You get 0.4771 by hand. So but that's what we want. We want not that, but 1 minus that, the probability of x more than or equal to 3. And what does that come out to be? 0.5229. Of course, that's doing it by hand. Now, you'll be able to do it by hand. By a calculator, what it look like. Now let's do the binomial distribution. I'm sorry, Poisson. Let's do it for 1. Lambda, just another way of saying the mean. 8, 0, and 0.06279. All right, right again. Should have my math right here. Let's do it for 1. 0.1738. Number 2. 1.2405. Right? So yes, my hand calculation matches the technology. To do it all in one fell swoop, not look for just one, I'm ready to look for a cumulative one. I'll use a cumulative one. Again, what's the mean? 2.768. I want to go from 0 to 2. That'd be 0, 1, and 2. And 4771. 4771. Look how it works. So that's A. Now B, what is the probability that game will end in a 0-0 tie? Well, a 0-0 tie means how many goals were done during the game? 0. There were no scores for either team. So for the match, which is the interval the Poisson distribution is set for, is for a given match, a zero score, a 0 goals means no one got a score. So that's 0-0. So C, or this here B, should be the probability of having 0 scores. So this is also the answer for part B. So part C, explain why you cannot compute the probability that a game will end in a 1-1 tie, but can provide an upper bound on this probability. Okay. So what does a 1-1 tie mean? Again, the interval is one match. X is number of goals during the match. So to have 1-1 tie would imply that there was X number of goals made. So a 1-1 tie implies that X is 2. But then again, so does a 0-2 and a 2-0 score game. It doesn't differentiate how the 2 is comprised, how the 2 gets there. It just tells you there's 2 scores. Maybe it's 1-1, maybe it's 0-2, maybe it's 2-0. So the best I can say is, what's probably of X equals of 2 scores in general. Scoring 2 was 0.2405. So the 24% chance, or 0.24 probability that 2 scores will be done on any given match. Okay. That's probably the best you can say is the best probability, or the highest chances of getting 1-1 ties is about 24%. But it could also be 0-2, it could also be 2-0. Because there's 3 ways to get a X equals 2. Now you could try and interpret it. Or maybe it's just split it by 3, so it's 0.08 for each of them. Fortunately, Poisson doesn't break it down to that type of discreteness. So yes, I can give you probability of 2 goals being scored, but whether it's a 1-1, 0-2, or 2-0, can't break it down that to that tightness. Okay. That's Poisson. Anything else I got there? I got some time still. No, I don't got time still. How about time? Okay, that's well, I'm pretty much out of time. So it's a pretty good overview of using Poisson, how to use it, when to use it. For binomial, how to use it, when to use it. Do you always keep in mind the complement, or 1 minus the easier number to get, or 1 minus the number you can get. And so let's have between now and I guess Tuesday. Now on Tuesday, I'll work on this problem set, and I'll be ready to answer any questions that may be on those problem sets and class on Tuesday. And I'll see y'all then. Same depressing time, same depressing, very sterile, non-friendly computer mix. But actually, I won't see you. Hopefully, you're hearing me though, and I'll hear from you and for anyone who wants to chime in for questions or anything. So, like I said, do the Launchpad section of 5.3. If you feel up to it, do the wrap-up section, do the quiz. Okay. Quiz, practice quiz, yes. And like I said, I'll see you on Tuesday. Tuesday. 9:30 online. I never could quite figure out how this thing works. Always seems to have more trouble than it's worth. It appears that way. Oh, yeah, everything. What's all this stuff up for? There you go.